In this paper, we investigated the Oracle query complexity of higher-order methods on smooth and possibly non-convex finite-sum problems. This is joint work with Rasmus King and Ahad Semakhan. We are interested in the difficulty of finding stationary points of functions that are expressed as a sum of n functions. Each of these functions is p-th order smooth, which means that it has Lipschitz p-th order derivative tensor. We further assume an upper bound on the initial gap to optimality. In each iteration, the algorithm can query one point and function pair and gets back any number of derivatives. This is a useful setting as, for instance, it comprises the popular problem of empirical risk minimization. First, we derive the lower bound for deterministic algorithms, which matches the known upper bound for any p up to constant factors. We did this borrowing techniques from convex optimization and applying them to the typical hard function used in the non-convex world. The key idea is to adversarially rotate the inputs such that the algorithm has to learn coordinates sequentially, exploiting the chain-like structure of the hard instance. This learning of coordinates is required for the algorithm to make the gradient small. Further, we investigated lower bounds for randomized algorithms. Due to the inherent randomness, the adversarial construction does not work anymore. Instead, we work with a probabilistic construction following prior work. Unfortunately, our bounds do not match the guarantees of the best-known algorithms for higher-order cases, which is a known problem in the first-order case as well. They might, however, suggest that variance reduction is more difficult in the higher-order case as the dependence on n is monotone increasing in p. In the first-order case, people have turned to mean-squared smoothness to close the gaps. Motivated by this, we propose an analogous second-order smoothness assumption. We assume that when picking a function uniformly at random, the third moment is Lipschitz continuous in expectation. Under this new assumption, we show that the SVRC algorithm retains its convergence guarantees while we can prove a sharper lower bound. To summarize, we have fully characterized the Oracle complexity for deterministic algorithms, but gaps remain to be closed in the randomized case. We believe that giving sharper lower bounds in a non-convex finite-sum setting opposed to the convex finite-sum setting is more difficult for technical reasons because the notion of success is stationarity instead of suboptimality. Eventually, we believe that resolving the gaps for all orders of smoothness will boil down to whether individual smoothness of the functions is more powerful for algorithmic purposes than moment-based assumptions.